everyone, especially to Dr. Maman and all of the fellows GAs. We are from Group 3 and we are going to present about the Bundi and South Bundi well interpretation of Petrel. So proceed to the table of contents. The first one we are going to talk about the overview of Bundi Field, project outcomes, project workflow, methodology, seismic stratigraphy, discussion on the finding of the maps, conclusion, and the last one is reference. So our team member are Yang Maizura, Muhammad Amir Hisham, and me, Aina Zulaika. Okay, hi, my name is Ain, and I'll be the first to explain about Malay Basin, or we can say that the origin of the Bundi Field. So, Malay Basin is located at the offshore of West Malaysia, or we can say it is located at the offshore of Terengganu, and it is located at the southern part of the Gulf of Thailand, and it is predominantly tertiary field basin. Malay Basin covered of an area for about 80,000 kilometers, and the sediments are filled up to 14 kilometers thick at the basin. So, other than that, Malay Basin is categorized under the shallow water basin because the water depth at the basin is basically lower than 200 meters. So, it is categorized under the shallow water basins. Okay, so last one is there are some tectonic events that lead to the formation of Malay Basin, in which the first one is the thermal subsidence during early Miocene to middle Miocene, and the famous extinction during the late Cretaceous to early Miocene, and last one is the compression during the late Miocene to Pliocene. Okay, proceeding to the overview of the Bundi Field. Bundi and South Bundi were formed by the combination of structural events in which I have explained from the previous slide, such as the thermal subsidence, the famous extinction, and the compression. All these three events have made some changes to the earth structures and creating a Malay Basin. So, Bundi and South Bundi have a sandstone thickness range from 3 meters to 20 meters for Bundi well, while 3 meters to 15 meters only for South Bundi. They are made out of channels and point bar sandstone that are deposited in lower coastal plain. So the age of this group is from the late Miocene and about 370 meter of thickness in Bundi, while South Bundi have a thickness of 399. So 3D Bundi Field seismic data has shown that it has a total of inline range from 250 to 1090, while the crossline range from 603 to 4003. The distance between these two wells is 4,704 meters. From the cross sections, we can see that South Bundi seems to be uplift because there is a fault that occurs along the horizon. Okay, as we can see, here are the stratigraphic description of Group E, in which occurs at late Miocene, all the sandstone interbedded with the shale and siltstone, and also the channel and point bar in lower coastal plain. All these three description matches the formation of the South Bundi and Bundi. So we know that South Bundi and Bundi falls under the group E. Okay, next I'll be talking about the project outcomes. For this project, we are correlating the seismic data and well data in order to generate a subsurface maps by comparing the two data of South Bundi and Bundi. And other than that, we are going to produce a seismic well tie from the 3D interpretation windows and to see the South Bundi and Bundi subsurface maps. So other than that, we are creating the fault picking and the horizon picking along the E32 horizon, and we'll be interpreting the geological features by the parameters. Other than that, we are creating a surface map in which the time and depth domain of the inline and X-line E32 horizon.
Hi, my name is Yamaisra Safira Mutimuddin from Petrol Science. Now I'll be presenting the project workflow. First of all, we are going to start with the preliminary studies, then data loading. Data loading are divided into two, 3D seismic data and well data, then well correlation, then well to seismic tie, then seismic fault and horizon picking. After done picking the fault and horizons, we are going to generate the structure map, then generate the depth map, then evaluate the stratigraphy and the structure from the depth map. Now I'll be presenting the methodology part. The methodology part is divided into 6. First of all is well correlation. Second is synthetic generation for wells and seismic well ties. Third is horizons and fault interpretation. Fourth is generating of TWT structure map. And the second last is generating the depth map. And the last part is to evaluate the stratigraphy and structure. Now I'll be presenting the more in-depth of each part in the methodology. First of all, well correlation. Well correlation is to correlate the horizon that is registered to the common depth. Secondly, synthetic generation for wells and seismic tie, that is to bridge the gap between the time and the depth dominant. Okay, by introducing a synthetic seismogram. So what is synthetic seismogram? Synthetic seismogram is a seismic trace at the well bore generated from the wireline log data. Thirdly, horizon and fault interpretation. First of all, we are going to interpret the fault. First, this is because horizons are displaced by faults once the fault is being interpreted. Then we are going to interpret the horizon. After interpreting the horizon, we are going to create the TWT map. TWT map stands for two-way time map. Now, the second last steps in the methodology is generate depth map. This is because we need to identify the depth from the produced data from the horizon interpreted, that is from the TWT map. Then the last step is to evaluate stratigraphy and structure. This is the last step of the methodology. After producing the depth map, we need to evaluate the stratigraphy and the structure. Now I'll be passing the floor to the next presenter for the next slide, that is discussion and findings. Thank you very much.
Hello, my name is Muhammad Hamid Rishad and I will talk about the interpretation for our project. This slide shows the location for the west and well top of Bundi and South Bundi. At the interpretation window, we can see the green one indicated for South Bundi and the blue one is for the Bundi. And the well top is indicated by the white square, which is E32 SST, and at 3D window, we can see the well for the Bundi and South Bundi is the one vertical one, and that's through the red sphere, which is the well top.
So proceed to the horizon and fault picking. There are two images that shows the result of the horizon and fault that we have picked along the E32 horizon. So for the left image shows that these are from the interpretation windows, while from the right image is from the 3D windows. Um, from the 3D windows, we can see that there are actually 8 faults, but only 6 faults that are found along a E32 horizon, while 2 more are found below the horizon.
Then we can see the surface map and fault picking. It shows this map shows the picket fault at the map surface, which is in time and that domain. This 3D window shows the better shape for the picket fault. In this view, the fault will be determined whether it is correct or not by we see the length of the fault. Like you can see at the top or at the bottom of the fault, which is either it is like curve or the flat one. The fault that's not correct is like zigzag. And we also can see the number of the fault is 8, and the fault length is range from intimate time is range from negative 1300 until negative 1750 milliseconds. And in that, the fault picking is range from negative 1500 until 2500 meter. Next, we go to the mat surface and fault surface. This is same from before, but the fault picking is converted into the fault surface. This view will show the shape for the fault, whether it is flat or curved or like other shape. As you can see in the slide, the biggest one fault, it have the curved shape, and the lightest one have the flat surface. Then in time domain, the evaluation time is range from negative 1900 until negative 3000 milliseconds. And in that domain, the elevation is range from negative 2050 until 2650 meters. Next, we can see the surface map or map window. This map window shows the surface map in the format of map window. This window also shows the detail of the map, such as the north arrow, the legend, the info box, and also the scale bar. For the depth domain, the elevation depth is ranged from negative 1350 until negative 1920 meters. For the time domain, the elevation time is ranged from negative 1300 until negative 1750 milliseconds. As the map is same, with just different in time, roughly the map shows the same thing such as the elevation of the map. And we can see at the northeast of the map has the highest elevation. And at the west part, it has the lowest elevation area. Then we go to the surface map, which is in 3D. This surface map shows the structure on the map, such as faults and also the counter values. On the map also, we can see the faults, which is the black and curved line. There are about 5 faults we can see on the map. Okay. This table shows the dead angle, the dead azimuth, type of fault, displacement of the fault, the length and height of each fault. So for example, for the first fault, the dead angle is 50.96 degree. The dead azimuth is 69.99 degree. The fault type is normal fault. The displacement for the horizon is about 65.40 meters. The length of the fault is 4193.69 meters, and the height of the fault for the first fault is 1630.99 meters. Also, that's also how to read this table. Then we can see the well section. This window is generated early in this project. It displays the well logs in specific order, available with available with logs, and also well top which in this project, which is E32 SST. This window shows for both Bundi and South Bundi. As you can see, the Bundi one is the blue one and the South Bundi is the green one. We can also see the distance between Bundi and South Bundi is 4,104 meters. Next, we go to the synthetic generation, which is this one is the Bundi one. Synthetic generation is the fundamental link between well data and seismic data, and it is the main tool that allows geological peaks to be associated with reflection in the seismic data. However, due to some error, our synthetic can't be generated. And this one shows the South Bundi part, which limited information, not like the Bundi one. Next, we go to the discussion of findings, which is the structural one. The first structure is the fault. A fault is a planar fracture or discontinuity in a volume of rock across which there has been significant displacement as a result of rock mass movements. Those are the example of faults which you can see at the inline 781. You can see the hanging wall is going downward and the footwall is going upward, and that is also the three fault here we can see. Next, this slide shows the time slice for the fault. This time slice is used to determine the deeping of the fault by looking at the strike and the dip of the fault. Then we can determine how to choose to pick the fault, either it is inline or S-line. As you can see at the slide, the dipping of the fault is like close to the inline section. Then we decide to choose to picking at the inline section because the fault will be more visible than when we pick at the S-line. This time slide shows at the z equal to negative 1550. Next, the structure is the folding. A fold is a type of originally planar surface, such as sedimentary strata that are bent or curved during the permanent deformation. An anticline is a type of fold that is an arc-like shape and has the oldest beds at its core. Then the syncline is the inverse for the anticline. At the S-line equal to S-line 3455, it shows the evidence of the anticline and syncline in the Bundi Field. And at the time slice z equal to negative 3604, we can see the shape of the syncline and anticline. When we look at the time slice, the structure, we can see the syncline or anticline that has the concentric circle pattern. Then that shows that there is the presence of folding at the syncline or anticline. Next, there is graben. Graben is a depressed block of the crust of a planet bounded by the parallel faults. Graben are formed when there are normal faults of opposite occur in a pair with parallel strut lines. Then we can see at the inline 491, we can see the evidence of the graben in Bundi Field, which caused by the normal fault, the opposite dipping of the normal fault.
Okay, so proceed to the discussion of findings of channel. The channel is linear, commonly concave-based depression through which water and sediment flow, and into which sediment can be deposited in distinctive, often elongated bodies. Channel can occur in a variety of morphologies, such as a straight, meandering, or even braided. So at the X line 809, we identified four channel that we have circled at the picture for the time slice at Z negative 842. We can see that there are channels that we have identified, and for the yellow circles shows the small channels which are also low sinuosity, while the yellow line shows a bigger channel which also has a high sinuosity shape.
Then we go to the discussion of finding, which is the stratigraphy. The first one is the sequence stratigraphy. Sequence stratigraphy is to subdivide the link and sedimentary deposit on a variety of scale and explain this stratigraphic units in terms of variation in sediment supply and variation in the rate of change in accommodation space. And we can see at the S line 3634, there are about 5 sequence of stratigraphy that we can get from this section. The next stratigraphy is the pitfall. The pitfall is the spurious anomalies, and then it can mislead for the interpretation for the seismic data. Pitfall can be associated with velocity, geometry, or recording and processing. And we can see at the inline 791, we can see the fault shadow pitfall which associated with the velocity. As we can see below the fault plane, we can see the seismization has that blurry part. That is the indicator for the fault shadow, evidence of the fault shadow. And also we can see at the S line 1951, it shows the pitfall, which is the diffraction. This diffraction is associated with the geometry. The next one is the reflection termination. Reflection termination is discontinuity recognized on seismic section that separate apparently conformable sedimentary units from non this apparently this reflection termination is discontinuity recognized on seismic section that separate apparently conformable sedimentary unit from non-conformable unit, forming the basis of seismic sequence stratigraphy. And we can see at the inline 1105, the black arrow shows the onlet above the boundary, and the red arrow shows the downlet. And the blue lines is indicate the boundary for this reflection termination. Next, we go to the discussion of finding, which is hydrocarbon potential. Hydrocarbon can be found in the seismic section by some indicators, and we can see at the S line 2809, we can see the bright spot, which is trapped by the fault. We can see there are about 3 part of this section have the bright spot, and both of them like under the fault, and it has like vertical one, which shows you can drill that the well at both that can penetrate both 3 hydrocarbon. And we can see at the inline 841, we can see the hydrocarbon is indicated by the reverse polarity, which is also trapped by fault. We can see the green one is the fault, and this hydrocarbon is trapped beneath the fault. As we can see at the seismization, that's about the peak polarity. The peak, then at the beside of it suddenly reverse to the trough. That's because you can see about 2 where the reverse polarity occur. Then we can see this is also this reverse polarity is indicate that there is this hydrocarbon potential that trap there. That's all from me. Thank you.
Now I'll be presenting recommendation. We have suggested several recommendations in this project. Our first recommendation is to make sure the data imported, such as well top, chair shot, or wavelet, are imported correctly. Second recommendation is to do a quality control when the result is obtained. Third recommendation is to use smaller intervals when doing the fault picking. Then lastly, use a wiggle seismic section when doing a horizon picking. That's all.
So for the conclusion, we can conclude that a Petrel with a full range tools could be used for interpreting some of the seismic features, such as possible faults, grabbing, channel, or even folding on the outcrops. And also, Petrel can be used to create surface maps. Other than that, maps that have been generated by the interpretation of the faults and horizon or time and depth domain. Um, Next, Bundi and South Bundi are the well top that I use in this project. Other than that, quantitative interpretation of generated maps and findings will give the information or and overview of the Bundi Field. Um, Last but not least, we conclude that the data that we get may contain um, many errors. So we think that by doing the quality control, we can minimize the error for the better outcomes. That's all from us, Group 3. I would like to take this opportunity to thank to Dr. Mama Hermana and also all of the lovely GAs. Thank you for helping us out throughout this semester in Tasman interpretation. And we hope that you guys are all in a good condition. And thank you so much for teaching us. Thank you.